A buffer is made by adding 0.300 moles of HC2H3O2 and 0.300 moles of NaC2H3O2 to enough water to make 1 liter of solution. The pH of the buffer is 4.74. Calculate the pH of this solution after 0.020 moles of strong base NaOH is added. Assume that in adding that 0.02 moles, the volume change of the solution is negligible. All right, so phase 1 to solving this sample problem is the neutralization of the addition of the NaOH. So we added NaOH. So the question is, was a strong acid or a strong base added? So NaOH is a strong base. And so which component of the buffer will neutralize the added substance? Well, acids are used to neutralize bases. So the acid HC2H3O2. So yeah, the acetic acid will neutralize the strong base. Okay, so I made a chart here to summarize what's going on before the addition, or before the neutralization, during the neutralization, and after the neutralization. Okay, and these are amounts in moles. Okay, so before the neutralization, we have 0.3 moles of acid, 0.02 moles of strong base, and 0.3 moles of our conjugate base from the sodium acetate. Okay, so we have our acid, our added substance, the water that's in aqueous solution, and then our conjugate base. Now, what happens during the neutralization? So remember from a few slides back, we said that during the neutralization, we have to assume that all of the strong acid or strong base that is added is neutralized. Okay, so that's why here I have minus 0.02 moles. So I'm using up all of the OH minus, the hydroxide ion, that was added. In doing that, again, what is doing the neutralizing? It's the acid that's doing the neutralizing. So I'm also using up some acid, the same amount. And when I combine the acid to the strong base, I create water and my conjugate base. So I'm creating more of my conjugate base, which is why I'm adding that to my initial amount here. Okay? So after the neutralization, I have 0.28 moles of acid, 0 moles of my added strong base, and 0.32 moles of my conjugate base. Okay, phase 2 of this problem is to use our new amounts of our buffered system, our weak acid and conjugate base, to find the pH at equilibrium. And so one of the really convenient things here is that we're dealing with a 1 liter solution. So I took the molar amounts from part 1, 0.28 moles of HA, 0.32 moles of A minus, and divided by 1 liter to get the molarity, which is the same. And then of course I create my ice table. So my change is minus X for the acid, plus X for the hydrogen ion and the conjugate base. And again, when we solve, we'll assume these changes are small enough to ignore. Okay, so we use the quantities from the ice chart at equilibrium to calculate the pH using our Ka expression. So I've written the Ka expression there. You will have to look up the Ka value if it's not given. So for acetic acid, the Ka is 1.8 times 10 to the minus 5, which equals hydrogen ion concentration, which we've called X. Concentration of A minus is 0.32, divided by the concentration of the HA, the acetic acid, is 0.28. So we do a little bit of algebra there to solve for X, and we get 1.5 times 10 to the minus 5th, 1.58. And then because X is the hydrogen ion concentration, we can take the negative log of that to get the pH, and we get 4.80. We can alternatively use the Henderson-Hasselbalch equation to calculate the new pH. pH is the pKa, or the negative log of the Ka, 1.8 times 10 to the minus 5, plus the log of the base concentration, which we found to be 0.32, over the acid concentration, which we found to be 0.28. When you do that, you get the same pH of 4.80.